The interaction coefficients, we are talking here about the electron interactions. So the stopping power, it refers to the rate at which the energetic charged particle, like the electron, loses kinetic energy as it moves through the medium. So this is concerning the stopping power of charged particles. of charged particles مثل الالكترون. Electron is a charged particle. The rate at which this electron loses kinetic energy as it moves through the medium, this is known as stopping power. We have what's called the total linear stopping power as total. So this quantity describes the rate at which the electron loses kinetic energy per unit length of travel in a material. It is generally expressed in a unit mega electron volt per centimeter. And as an equation, it's given by this equation as total or total linear stopping power equal dEk over dx. So E here is the kinetic energy of the incident electron. X is the path length. S هي the path length in the absorbing medium. In practice, this is calculated for a given material. This is calculated for a given material and electron energy to determine how rapidly an electron loses energy as it travels through the medium, through the tissue. So شو هي؟ بس قول الريت يعني depends on time. So rate at which this electron loses kinetic energy. Another quantity is the mass stopping power. Now, to account for the effect of material density on stopping power, we can introduce the mass stopping power. We can use this quantity, the mass stopping power. كدefinition بتعبر عن total linear stopping power divided by the density of the absorbing medium. And here we divide as total over rho. Rho is the density. هلا total mass stopping power كسيمبل هي او كدefinition هي S over rho equal 1 over rho dEk over dx. dEk over dx هي S total linear stopping power. هلا إذا قسمت على density of the absorbing medium, we get the mass stopping power S over rho. So the mass stopping power is typically measured in mega electron volt centimeter square per gram. It represents the energy loss per unit mass of the absorbing material. So this is the total mass stopping power S over rho. It consists of two components. And the total stopping power of an electron فعليا هو السميشن of two major components يلي هن the mass collision stopping power and the mass radiation stopping power. مثل ما حكينا قبل انه we have in one of the previous slides we have collision interaction and radiation interaction. So كمان here concerning the electron interaction we have also mass collision stopping power and mass radiation stopping power. So we have a combination of these two key components. The mass collision stopping power he S over rho collision. This component arises from orbital electron interactions. So when the energetic electron interacts with orbital electron in the material, It can cause atomic ionization or atomic excitation. Atomic ionization يعني الانسيدنت electron transfers enough energy to eject an electron from its orbital shell leading to ionization. بينما atomic excitation, this is concerning the energy transfer. If this energy transfer is insufficient for ionization, the orbital electron may be excited to a higher energy state. فهذا الفرق بين ionization و excitation. So these interactions result in energy loss from the incident electron. The mass collision stopping power reflects this energy loss, and it is a dominant component at lower electron energies. بالنسبة للكومبوننت الثانية اللي هي الماس radiation stopping power S over rho radiation, this component arises from electron nucleus interaction. فإذا هون حكينا عن interaction بين الالكترون والorbital electron، هون بنحكي عن interaction بين الالكترون والnucleus of the atom. بهيدي الكيس بالماس radiation stopping power brimstolling radiation is produced. So we have brimstolling production. So the total mass stopping power is the summation of these two components. S over rho total equal S over rho collision plus S over rho radiation. So stopping powers are rarely measured and must be calculated from theory. We cannot measure these quantities. We can calculate them. This is the first point. فإذا the most commonly used theory to calculate stopping power بسميها beat theory. So a beat theory is a method to calculate the stopping power. It is particularly useful for soft collisions. يعني لما بيكون عندي low energy interaction بين الالكترونز والorbital electrons. So for البيت formula أكيد بتعطيني detailed calculation of the stopping power for ionization and excitation. For electrons and positrons, the energy transfers due to soft collisions are combined with those due to hard collisions using the Muller and Baba cross sections for free electrons. So these methods are concerned with high energy electrons. So لما نحكي عن electrons أو حتى عن positrons. To complete mass collision stopping power for electrons and positrons, or the complete mass collision stopping power for electrons and positrons is taken from the ICRU report number 37. شو بيقول هيدا الريبورت؟ So according to this report, can see this formula. هيدي بتعبر عن الماس stopping power for electrons and positrons. هلا بيفرق شيء بسيط يعني for electrons for positrons. كيف بتفرق الايكويشن؟ بيفرق معي مثلا F minus وال F plus. الF here F يا بتكون minus يا بتكون plus. So F minus هنحكي for electrons it is given by this formula. F plus for positrons is given also by this formula. So S over rho اللي هي mass stopping power depends on multiple parameters, depends on NA, Avogadro's constant, Avogadro's number, depends also on the atomic number of the material, Z. It depends strongly on Z. It depends on A, the molar mass of the substance. RE, the classical electron radius, MEC squared, the rest energy of the electron, beta, which is mu over C, C هي velocity of electron, C هي velocity of light, V هي velocity of electron. I is the mean excitation energy, delta is the density effect correction. إذا هدول الثيوريز are used to calculate the mass collision stopping power. طبعا we can we just need to understand and to know the parameters within the equation. In the study of the interaction of charged particles like electrons and positrons with matter, interaction of these particles with matter, so mass stopping power plays an important role in describing the rate at which these particles lose their energy as they travel through the medium. The mean excitation potential I, this is the critical parameter used in calculating the mass stopping power also, to calculating the mass stopping power for electrons and positrons. It represents a geometric mean value of all ionization and excitation potentials of an atom of the absorbing material. So these potentials are the energies required to eject an electron from the atomic shell, نحكي هون بالionization, or to excite an electron to a higher energy state, نحكي بالexcitation. So I values are usually derived from measurements of stopping powers in heavy charged particle beams, for which the effect of scattering in these measurements is minimal. So these measurements help minimize the scattering effects, allowing for accurate determination of the excitation potential. For elemental material, I varies approximately linearly with Z. We have a linear relationship. I equal 100.5 times Z. So I depends on Z. They vary, I and Z vary linearly. For compounds, I is calculated assuming additivity of the collision stopping power, taking into account the fraction by weight of each atom constituent in the compound. هلا الهاير I levels, if we have higher I levels or higher I values, يعني which correspond to elements with high atomic numbers حسب equation, this result in higher ionization and excitation potentials, and this lead to higher mass stopping power for charged particles. بينما إذا عندي lower I values, this correspond to materials with low atomic numbers مثل الهيدروجين مثلا, مثل الكربون, where here the electrons and positrons undergo fewer ionization and excitation interactions, and this will result in lower stopping powers. So this parameter I, the mean excitation potential, is important to understand how these electrons and positrons interact with different materials, especially in fields like the radiation therapy and the particle detectors. We have here, for example, selected data on the mean excitation potential I, as given in ICRU report, for hydrogen, carbon, nitrogen, oxygen, air, water, liquid. So we have different excitation potentials. The values are in electron volt. This is concerning the interaction coefficients for electrons. So electrons interaction. كمان في عندي point تاني اللي هي الphoton interaction. So second part in this point هنحكي عن interaction coefficients but for the photons this time. بدنا نحكي عن الفوتون interaction. In photon interactions, the energy transferred to a charged particle is referred to as the energy transfer. So هيدا الشيء هيدي الديفينيشن اللي حكيناها قبل. The energy that is transferred in a photon interaction to a light charged particle. هنحكي عن mostly secondary electron مثلا. This is called an energy transfer. This process is critical because it involves the conversion of the photon's energy into kinetic energy of charged particles, such as electrons and positrons. The amount of energy transferred is quantified by the energy transfer coefficient. This is denoted ETR. So ETR is the energy transfer coefficient. هلا هيدي البار اللي موجودة هون بتدل على average quantity. So ETR bar is the average energy transferred from the primary photon with energy h mu to kinetic energy of charged particles. الانرجي ترانسفير اكيد بتعطيني معلومات عن الefficiency with which the energy from the incident photon is converted into kinetic energy of charged particles. So بالphoton interaction, a small portion of the energy transferred to charged particles such as electrons during their deceleration results in the emission of radiative photons. So a small part of the energy that is transferred in a photon interaction to a light charged particle leads to the production of radiative photons as the secondary charged particles slow down and interact in the medium. كمان leads to here Bremsstrahlung radiation. حكينا عنها كمان مطولا. يعني عندي two factors هون. هنحكي عن the production as secondary charged particles. كمان نحكي عن interactions which are prominently the Bremsstrahlung radiations. هدول بنحصل عليهم بسبب الكولوم field interaction بين ال charged particle والatomic nuclei. So this loss through radiative processes is represented by the factor J bar. هيدي الجي بار اللي سميناها radiation fraction. The remaining energy is absorbed. So loss بنعبر عنه بالفاكتور J bar بينما remaining energy is absorbed. This process is described by the energy absorption coefficient mu En. So mu En equal mu Tr times 1 minus G bar. شو هي الميو تي ار؟ هي الانرجي ترانسفير كوفيشنت. الجي بار هي الفاكتور يلي حكينا عنه من شوي اللي هو الراديشن فراكشن.